Hi all, I'm Sachin, like as you all know, and yeah, like today I'm going to talk about RL for reasoning. So let's first like define what is reasoning, because like it has all over the place, everyone thinks that reasoning means something else. So let's first define what is reasoning. So reasoning is solving tasks where extra thinking time or compute helps you find better answers. So how do we do usually reasoning? How to do reasoning? Prompting, like initially prompting was like few short chain of thoughts that you provide like bunch of examples of like reasoning traces and then ask language model to reason based on them. Then people figure out just by like letting it say, hey, let's think step by step, or like let's take a moment and think deeply or something like that. Like instruct language models were able to do some sort of reasoning well after that. Then people figured out how to do that with supervised fine tuning. So work tokens or scratch pads and like scratch tokens were used to define like show the reasoning traces, and like those things showed really good performance. Like these again, like these SFT techniques, work tokens, scratch tokens, they are from like 21-22. Like Galactica introduced the work tokens. Scratch tokens were introduced by some scratchpad paper in I think somewhere mid 21 or something like that. And the third option is like using RL or search algorithms with like either outcome reward models, process reward models, something like Quiet Star or O1 slash R1. Like we don't know how O1 R1 like works, but I'm just gonna throw a bunch of guesses today. So like the way they did supervised fine tuning for reasoning is this is the scratchpad paper, like work tokens were introduced in Galactica paper, and here in general if we can see there is like scratch start scratch end token over there, work start work end token, and all the reasoning traces are in between them, and they have manually like annotated all of these things. They have manually like paid people bunch of money to actually get these reasoning traces and showed that performance is like really great. Rather, if we see Galactica's performance on math and like in general GSM 8K compared to at that time state of the art was like kind of Palm 520B, Galactica punched way above its weight, and I think it was better than Palm, or it was close to Palm's performance while having like around 20x less parameters. But there is limitation, like the what we were talking about. The reason like this is just slightly better than like having like chain of thought or like asking it like let's think step by step and that way is because internet has like these reasoning steps, but like it often misses steps in between. Like those reasoning steps are for us like humans to understand, so all the minute computations which occur in between, they are usually missing. But for transformers to actually work and like do this sort of reasoning, having those small like minute in-depth reasoning steps is much more necessary. It is particularly missing. Also like another limitation with this SFT is like usually it is very linear chain of thought, that this is the step, then this is the step, then this is the step. Sometimes while thinking we go down some rabbit hole, go a couple of steps up, diverge, like all of that, like graph search or like thought search is not present in like supervised fine tuning data sets. So that's the not present in data sets as well, plus on the internet scale data it's definitely not present. Another thing is manual data labeling is expensive. Like we all have heard the stories where OpenAI pays like $1,000 per hour to like PhD data labelers, and it is hard to scale over across all the domains. So these are the major problems with like generating data through supervised fine tuning. Like can RL come to the rescue? And this is the talk about RL and how it is going to come to the rescue. A quick overview. Supervised learning is hot dog, not hot dog. RL is playing a game. So over there, we know only the correct actions, but because of that, we can have a like really great like gradient flow feedback. With reinforcement learning, there are no correct like actions. We have to perform an action, evaluate it, and get a respective reward with about that. In supervised learning, it is usually one-step prediction. With RL, we usually have multi-step predictions where environment is usually non-stationary, and like in supervised learning, our assumption is every data point is IID, independent and identical, so identically distributed. Here usually data points are highly dependent on each other. Whatever action you took in the past is going to impact your future actions. This is in general RL framework where environment provides you with state, agent looks at the state, performs an action, and based on that action environment provides the reward and the next state. and we here learn from interaction to achieve a goal. So with now coming back to the problem statement where we are using RL plus LLMs, what can be the state here? Usually the state is going to be whatever user prompt we have come across plus all the generated tokens till now. Caveat here, the case which we are talking about here is usually like one like single turn question answering. We are not talking about multi-turn question answering where user asks a question, model answers that, then user asks a clarifying question, and here model is trying to get something done from user or like help user in achieving some sort of goal. We are not trying to optimize for that case right now. We are constraining our problem towards where it is a single turn. User asks for any question, can be an extremely hard mathematical question or something, but a single turn user prompt comes in, model gives the response back. So we are for now just restricting ourselves to this particular setup. What can be the actions? Actions can be a finite set where like the tokens which you output from your vocabulary is your action, and you can think at the set of like after outputting every token, you can think okay, you can use RL policy to evaluate what the next action should be. Or otherwise, you can have an infinite action space where rather than reasoning over every token, you can reason over thoughts. But how do we sample thoughts, or how we understand where thoughts are beginning or ending? So we can like train our instruct models to either end the thoughts with like new line or dot or like semicolon, something like that. We can train our like actor LLM to give the thoughts in this space. So where do these rewards come from? We talked about what the state is going to be, what actions are going to be. Now what rewards can be. Like there are three different ways for that. First is vibes. Like do I like the answer or not? That's literally the entire premise behind RLHF. Like reinforcement learning from human feedback. So which output human liked, that's it. Like, and based on that preference data set, we train the model. So RLHF is literally for vibes, and because of that it gives you like very good styling. Like some people like Claude's outputs better than ChatGPT's outputs, even though they are saying the same things. Probably because Claude has optimized for that styling much better compared to ChatGPT or even Llama. Another second option is self-consistency. Now we are coming to the domain where maths or coding, some sort of scientific problems are there. We don't know like whether particular output is correct or not. So we can sample the same LLM with the same question, probably hundreds of times, and figure out like trust that LLM will get to the correct answer most number of times. And based on that, like whatever answer, like we just do like n sampling, and whatever the answer we get maximum amount of time, that can be the correct answer, and like we can propagate like if that answer is correct, we can use that as a reward, like based on that difference. And third is like reward from external or verifiable environments. Specifically in case of like if we can have some sort of solver or some sort of like external verification systems, which can be Python code interpreter. It can be like if we have some sort of like theorem prover, it can be that. It can be all of these different things. And in those specific cases, like reward from these external and verifiable environments can train our like can guide our reasoning process, can teach our large language models to do these things in a much better manner. We usually like we can have external ground truths or external oracles, but we usually do train reward models to approximate this external environment. There are these two places, but again like assigning rewards and figuring out how to provide this sort of incentive structure is in itself like as much art as science, because if you mess up assigning rewards like in a proper way, then reward hacking can happen, which is like Goodhart's law. When measure becomes target, it ceases to be a good measure. Specifically in the case of RLHF, like when people like overfitted on the RLHF data, and like when the reward models did not get aligned properly, in this case of like long form QA tasks, like LLMs learn to generate just long answers because they thought like if we write long answers, we get better reward. It is kind of like our like board exams or something. You write so much that you get better reward at the end. And like they learn that how to use like consistent logic but generate incorrect answers, like if you haven't like tuned your reward models correctly, or generate coherent answers but with subtle fallacies, and like some sort of such hallucinations even with like coding tasks. Like if you don't assign your rewards properly, if you don't massage or shape your like structure of rewards properly, then all of these issues can happen. Like Lillian Wang recently posted a blog post about reward hacking, so I would highly recommend everyone to read that. She talks about how this happens in LLM space, how this happens in general RL space, and what can we do to avoid this from happening. So RL methods, like in general, like there can be different ways to solve RL problems. Some of them are like evolutionary methods like black box optimization. Some of them are like dynamic programming, Monte and like other search methods. But if we just focus towards like RL methods where we are using RL as an objective function to like generate the gradients and change the weight of the networks, we have usually like two major families: value based, which is all DQN and all of the like descendants of DQN methods, A to C and all, like no, not A to C, my bad, DQN and all of that. And some of them are policy based. Like policy based are like reinforce, PPO, A3C. These are all policy based. And where policy based and value based methods interact with each other is actor critic. So A to C, asynchronous actor critic, like A3C is asynchronous advantage actor critic, or just advantage actor critic. These are actor critic methods which use value based methods and policy based methods and merge both of them. Value based methods, you calculate the value of state, that if I reach this particular state, what's the expected future reward I can get from this particular one. Like let me actually show you. So this is a value function. If any of the like if your reinforcement learning methods, forget everything else, only look at this Q function. This is a value based function. So if you are calculating, if in this state, if I take this action, what would be my future return? Like if you are doing that calculation, you are probably using value based method, either like state action, or like if I reach this particular state, what's the future value of that state? And this entire thing is a policy based method. This is a policy gradient theorem, where like if you guys remember a couple of days ago we learned about like energy based methods. This looks like very close to energy based, because here we are trying to increase the energy for like decrease the energy for higher Q values and increase the energy for lower Q values. So this is like in general gradient ascent method where we want to increase the Q values, and this is in general our traditional policy gradient method. Reinforce, PPO, A3C, all of them are variants of this. So like in reinforce, rather than having this Q, if we do Monte Carlo, that we just keep running things in the forward, and whatever return we get, we empirically get, if we substitute that here, that becomes reinforce. In PPO we add like a bunch of other terms, like we add advantage term and like it becomes PPO. So it is like they all are interrelated. So availability of sampling actions, like again if we go back to this is a standard like RL diagram, that if we know, if we can sample multiple actions and see that in this action we get this state, and if we can do rollbacks, like which we cannot, like this part, like width of depth is not available in robotics. We cannot do an action and roll back, but in language modeling we can do this. So that's the difference. So in width of update, if we can do that, we can just do dynamic programming at single update. At multiple level depth, we can do proper search. Same over there, Monte Carlo is like if we can't change something, you can just run your trajectory in robotics and you get Monte Carlo estimations. TD learning is usually you do one action and you estimate, okay, what's the reward of like, or what's the value function of that specific state. In terms of like LLMs, how does this translate? Monte Carlo looks like chain of thought, that you got the state, now you are just going to unroll the existing policy and hopefully reach to the correct rationale and correct answer in the end. Exhaustive search looks like tree of thought method, where like you had the prompt, you sampled bunch of thoughts, figured out, okay, this thought seems interesting, followed that thought below, like among those things you like explore which thought to do, but for doing that you need a really good value function, otherwise this search space is never go, like it's infinite. Like finding a right answer is going to take a long amount of time. Dynamic programming looks very close to, not exactly, but still looks very close to Quiet Star to me. So in Quiet Star you randomly sample a thought and then like but for every token you sample a thought and you ensure that like is adding this particular thought helping me with the generation of the next token or not. If it is not, you disregard that. If it is, you use that particular thought to fine tune your LLM, and by that method you kind of like get some sort of like dynamic programming sort of reasoning process embedded in your weights of large language models. So like all the methods we talked about till now except exhaustive search, these are all reinforcement learning methods, how we can use RL to like fine tune LLM, to actually change the weights of LLMs and such that the resulting LLM becomes better in reasoning, and like all of our reasoning are still going to be single shot. It can consume lot of tokens, but it is still going to be like one shot example. Like you give like even in ICL or few shot examples, like it is still like from an LLM's point of view or from inference point of view, it is a single shot thing. You give a prompt, it generates an answer for you. Can we do something different, which is like exhaustive search? So search, which is like scaling test time compute. If we have more and more amount of time and compute available, as we saw in the like definition of reasoning, if we have more time available or more compute available at the test time, if we can get better answers, that is reasoning. So RL helps us do those things using like our network's weights, network's parameters, but in the space like with using search, we can do that without changing the weights of our network in the test time. The bitter lesson was the two methods that seem to scale arbitrarily as our compute scales are learning and search. We have seen how learning works, how we can fine tune and like using the gradients change the weight of the network and like ensure that network learns all of these like complex reasoning processes. What can we do better is like with search, something another dimension which can scale rather than just scaling the like learning process. Specifically here we can scale because we can sample multiple actions and roll back those actions with respect to LLMs. We are not like committed to the action, those specific actions per se. Yeah, so because of that we can perform search here. And another advantage of doing search is like LLMs are supposed to, or like we have seen that they know almost everything which is there on the internet. They are extremely good memorizers, they have all the knowledge in the world. Now our job is to just ensure that how we are sampling the correct part of from their knowledge base. So like because of these things, like search becomes a very like promising and interesting new direction to explore. But again, like we need better reward models or value functions to guide the search. Otherwise, we can like even just doing BFS at a single prompt level, we can generate literally millions of thoughts. And like that tree search, that tree is going to be like insanely huge and we cannot like navigate that tree properly. So we need some sort of better reward models to actually guide through this thing. People are, OpenAI has had hinted that they do search, but like we will talk about whether they do or not at the end, like this thing. But search is the like, it looks like a next holy grail and like everybody is trying to make search work with respect to LLMs. And at the same time, like I'm not sure whether I mentioned this or not, but specifically for like reward hacking, like it is a known fact that you don't overfit on your either preference tuning data, or even after you get preference tuning data, you don't overfit PPO based on reward model. Because if you do that, like large language models are known to hallucinate and do have all of this degenerate behavior. So like reward models are extremely like finicky behaviors. So you train for 1 or 2 epochs, you stop, use that reward model on like 1 or 2 batch of PPO, like then get another batch for like training new reward model, train another set of PPO. So like reward modeling and PPO, these are like cyclic processes. Yes. So this is the specific thing. They initially trained like a pre-trained a transformer model, like some 1 billion and 2 point some billion, like they trained 2 transformer models of that this thing using like generated a bunch of synthetic data and trained on that with synthetic data, like pre-trained the transformer models to predict world model that after this state and this action, what new state we can see. In chess, it is very easy to predict. This state, I move this piece there, this is the new state. So they trained to predict the world model, value function, that what should be the value function. They used stockfish to generate this, like lots of synthetic data and generated the value functions, and learned the policy also, because like they didn't learn they learned value function by like tokenizing the values, because having a continuous values like is very hard for like softmax based transformer to predict that 54.5 and 54.4 are how different. It is very hard because it's a categorical distribution. So they categorized the distribution in like 64 buckets and decided that value function will predict one of those buckets, that okay, in this state this is the highest bucket, this is the second highest bucket, and such that. And also learn the policies, because if multiple states, and they trained policy function as well, because they wanted to ensure that they pick the correct policy when because of discretization, if two states give the same, two actions give you the same bucket, which should you pick? For that they trained policy also. And then they did external search, which is Monte Carlo tree search, to train, and they got like amazing performance boost. Like the one thing which they explicitly talk about in this paper, this is a DeepMind paper, that like doing a forward pass through like few billion transformer models is expensive. If at every step you are gonna, in Monte Carlo tree search, you do like in alpha 0, you do few like hundreds of, like tens of thousands to millions of simulations. Doing that many in every step is gonna be insanely expensive. You can't do that when you have such a big like transformer models. Like, so they show that how to condense these things, and how to like we can have around like 100 to few thousand simulations at each step. This is in general like Monte Carlo tree search, which they use like rather externally, that in this state these are all the actions available. And they take the they explore few actions, and in the end they run the policy and get those actions, like get those values back up, and do like they do some hundreds of these simulations, and you can see the performance gain here. So like stockfish is like basic stockfish is here. MAV is their transformer. Like it is 1259 to 1367 based on how you pick up the policy. So mean scoring and max scoring are those things. But like this is your general like pre-trained transformer. Once you do like with 100 simulations MCTS, you get around at least like 100 ELO score bump. And if you do that as your simulations go up 2000, you get like a significant high like international like ELO bump. So like you can do this externally. They taught transformers to do, like distill this search process in the transformer. As we initially said that like rationals are very linear. They don't have like branching, they don't have all of those things. Can we learn those things? That was what stream of search, oh I ate the F, but that's what stream of search paper showed. These people showed that like transformers can learn to do this sort of search mechanism, and like whatever this external Monte Carlo, this entire pipeline, like they learned to do it in context. They fine-tuned transformers on these like traces. They learned to do this in context. It works very well, but at the same time, the problem is here you are consuming context space, context length, whatever tokens you are generating for this search. And because of that, like it works pretty well with smaller number of simulations, but as your depth of the game increases and number of simulations increase, this is not going to work. So is Owen doing the search? Probably not. Like this article like dissects it pretty well. Like it still feels like Owen is also like doing much better chain of thought with respect to like learned reinforced, like they have used RL in much better ways with internal reward models to change the weights of the neural network. But in like test time search, probably like Owen is not doing that. That's what like interconnects.ai says. So the paper which came today, so I wanted to add it here, the coconut paper, that reasoning but with uninterpretable vocabularies. Like what this paper does is like rather than predicting the next token, like when you want to generate your reasoning, you like do start of thinking token, at the end you do, and when the grid is greedy decoding tells you that end of thinking token has got good probability, you output end of thinking token, and then you again go back to natural language decoding. In between those things, rather than passing the token and token embedding to for in the autoregressive phase, here you don't sample the token, you extract your unembedding layers activations and you pass them on as your like next token embeddings. And yeah, like they claim that it performs like kind of like BFS, like breadth first search, rather than committing to a single path with like when you pick up tokens, you have to kind of go down that path. They commit that, they say that, and like is latent space better for planning? Up to a certain degree, I believe yes, but like the major challenge over there is going to be here we can kind of guide, we can understand the reasoning and we can control the reasoning. In latent space, how are we going to control the reasoning is going to be much harder thing. Like probably we will be able to give proper rewards and latent reasoning like in the like as we scale things, these things might be much better rather than forcing them in like natural language, but we don't know that yet, and like this is still an active area of research. And yeah, like the last thing is like can we do reasoning? We talked about reasoning with LLMs. Can we do reasoning with VLMs, vision language models? Like is Bangalore north of Chennai? Like I don't think our vision models are able to look at this image and figure out which city is in the north and which city is like in the south. So we still have some amount of like reasoning in like vision space